Hello everyone, and welcome to Nanorooms after a long time. So, I have a fun question for you guys. I have a flash, I have a pacemaker, and I have a timer. A electronic timer that's used in older electronics. And I'd like to ask everyone here that's listening in the audience, well, what do these things have in common? As Grant might say, well, pause and ponder. Other than being electronic, of course. Well, okay, I'll assume everyone has the answer inside of their head right now. So, these things involve discharging electricity in some way or another. The flash has to store up energy and release it in one brilliant flash. And the timer and the pacemaker need to charge and discharge periodically to keep either the human or the computer functioning. So, what's the secret here? How do electronic devices store and hold charge? Not only that, but how do they charge and discharge rapidly? Well, the obvious answer is definitely the battery, right? Batteries. Well, not so fast, because batteries do in fact overheat, blow up, and degrade with rapid charging and discharging. Considering how fast the heart goes, or even so the computer how fast it goes, the battery is definitely not a viable option for storing and releasing energy rapidly. So, what is this mysterious component? Those of you who have taken EE, well, it's for those who actually guessed the battery, here's a consolation prize. Um, you weren't that far off. Turns out that Mr. Battery here also has a cousin, and his name is the capacitor. Capacitor, as in capacity to store. So, the way these two differ is that, hey, batteries store energy as chemical reactions, while capacitors store them as actual charge from electrons. So, the way you charge them, well, it's exactly like a battery. It's like attach it to a power source and it charges up. And with no more power, it will just discharge back. And it can do this really rapidly. So, what if you play a little trick on it? We talked about charging and discharging rapidly, right? So, actually, there is a type of electricity that allows things to be discharged and discharged really, really rapidly. And that thing is literally probably right next to you right now, and that's actually the outlet on your walls. Yes, you're correct. That's correct. The outlets are actually something called AC current, or alternating current, where the voltage and the current goes up and down. Basically in a manner where you plug anything, it will discharge and discharge, charge and discharge. Well, what will happen to the charge inside the capacitor? How will it charge and discharge? That's the question. Maybe let's put a little bit of physics in there. That could help us. If you actually try building this circuit right here, where there is the outlet, the resistor, and the capacitor, you'll find that the voltage of these components always adds up to the power source. If you add the voltage of the resistor and the capacitor together at any time, it will always equal to the outlet at that time. Having a mathematical mind, well, let's try our hand at modeling this system, shall we? Let's try to actually find exactly how much charge there is inside of the capacitor. Maybe we want to tase someone with, I don't know. So, looking at the models describing the voltages online, you come across these two. The source we'll cover later. We'll find that the voltage across the little resistor is current times resistance. That's Ohm's law from, middle school. And the capacitor is charged over something called capacitance. So, now, since we're dealing with a power outlet here, let's actually assume the AC current to be a sine wave. Let's not complicate ourselves. Don't put linear combinations in there. Let's just go with a regular sine wave. V of 0, the maximum voltage, times the sine of t. So, as we know from earlier, these two add up to be equal to each other. But wait a minute. From middle school, you've learned that actually current is just the rate of charge flowing. So, wait a minute. That means we actually have a differential equation, right? The rate of charge flowing is just the derivative of the amount of charge there is in the system. So, that means that we can have a differential equation. That actually looks a little bit easier now, doesn't it? So, as someone who likes math, the coefficient, or physics, or just anyone that matter, we really don't like coefficients, so we're just gonna cancel them all out and pretend they're all 1s or 0s, whatever makes sense to simplify this entire thing to just 3 terms. And since this isn't actually current, this isn't actually the capacitance, this isn't actually the charge anymore, we're just gonna rewrite this thing as x. It's a charge-like thing, but it's just been warped. The units have all been warped. So this should actually be easy, right? From anyone who have taken Calc 1, just, write this into the differential form and let's separate and integrate. But wait, hold on. Oh, we actually don't know what the integral of x dt is because we don't have the explicit form of x. So, that means that we can't actually do the separate and integrate trick. So, what do we do now? Well, we want to find the answer. So, since this is a very engineering topic today, so let's be a little bit less strict here and let's do some engineering magic. That's right. We're gonna be absolutely approximating this entire thing. Well, first off, x dx dt actually feels like a slope, right? So let's choose a random point in the positive region, of course, and a thing will have the value of x of t. And now let's find what the slope is at that point. That's not that hard, right? We have the x the charge thingy, and the time. Plug that into the equation. We can find the slope. You can find the x by dt at that point, right? So, what we're gonna do is we're gonna step over a little bit by a delta t. I've drawn it so big just because it can make you all see, but in reality, delta t will be really small, like 0.01, 0.001, no matter how, depending on how much accuracy you want. So, now, let's move the point over. And now, the point has landed at point x of t plus delta t. So now, you get the theme now, right? Let's repeat this thing. We've arrived at a new point, and we're going to find a new slope. Now, when we found the new slope, we're going to move the point along that slope, but no more than delta t. So, we do this on and on and on until we're pretty much satisfied with how much of the solution we actually want. So, how about this? Since the method actually approximates quite nicely, the more delta t you shrink, why don't we actually try to draw out all the possible slopes while we're at it? Let's also draw the direction in them all as well. This is what we call the direction field. This field can also be written in vector form since, we're already going with directions and magnitude, so that actually comes out to be a vector, right? So, this is what the vector, those little vectors actually are. We'll get back to this later. No need to actually fuss over the details. If you didn't get any of that, well, let me give you a nice analogy. The direction field is like a river. You toss those little white pebbles into the river, and they actually just flow along the plane like a river. The river will push the pebble along. And the neat thing is that the path that those pebbles trace are indeed the solutions to our differential equation. So, the only caveat is that you just only need to know the amount of charge inside the capacitor beforehand. This is what we know as its initial condition. Initial being first and condition being, condition. So it's conditioned to have some amount of charge inside of it at first. So, well, the thing that really makes me feel a bit unsatisfied now, even though I said I'm gonna go easy, it still feels a bit iffy that we're approximating. Because in the end, you still, to find the explicit form of x of t, the more the more I look into it, the more I want to find the explicit form of x of t. You still need to integrate it to find it, which, well, is a lost cause, as you've seen earlier. Well, by all means, try to prove me wrong that you can't integrate directly. But, well, I have an alternate path to show you guys. One that will end up not only giving you x of t, but it will also be one of the most elegant things I've actually studied in calculus so far. And this is owed to brilliant.org, by the way. The little thing we can do with the vector field is that we can rotate it by 90 degrees. Instead of vectors being tangent to curves, they're now perpendicular. Nice. And as you can see on the screen here, the vectors are in the same place, just rotated. Well, wait. Doesn't that really... Why would we do that? Doesn't that really make the problems 10 times harder now? We had a tangent, now we have a normal vector. It doesn't make sense to do that. It makes it harder. Well, be patient. You'll see soon. So, let's interpret the field first. The colors actually code for something. The yellowish bits in the middle just means the field is increasing just a little bit in that area. But if it's red, it's increasing a lot. So, doesn't that tingle your your visual intuition a bit? Just maybe you can draw a surface over this that increases based on the size of the arrows and the magnitude as well. If it points away, that means it will go up. And then the more red it is, the more height it gains. So that conceptual surface thing looks like this. As you can see, where it was red earlier, it was really, really steep. And where it's yellow earlier, it's not that steep. For those of you who are quite observant, you actually see that the curves that trace out the solution, they're always actually the same height from the ground. It's like trekking a mountain, but you make sure you never climb up nor you go down. You never change your elevation. So, if I'm getting this straight, as you can see here, the solutions, they're actually there on the graph already. If you can know what f of this function is, I'm going to call it phi. If you know what this function is, if you can extract that function somehow from the differential equation you have, can set it equal to something, some sort of constant. As you can see, these constants right here, phi equals 0.5, 1.5, 2.5, 3.5, actually corresponds to our initial conditions earlier, right? So that means that if you set phi equal to some constant that corresponds to our initial condition, we can use that to come back and solve for x of t. Maybe you can do that, right? That would result in, well, getting rid of a complicated calculus problem into simply just algebra, simply functions. So let's recap a little bit. We try to approximate the solution using slopes. Then we plot them all over the board using direction field. And, well, we call it direction field. If we drop some pebbles onto the field, the path that those pebbles trace are actually the solutions to the equation, though this is just an approximation. And we tried something funny by actually rotating the field by 90 degrees, then trace that into a function, which might actually hold the answers to our problem. So now, let's work backwards a bit. Doesn't the relationship between the function and the vector field kind of feel familiar? this kind of feels like a slope, right? When I said earlier. I mean, the steeper the function, the larger the redder the arrow gets. And well, if you had that kind of intuition, you're on the right track. Well, more rigorously, the thing is actually called the gradient. It's kind of like a 3D slope. So, the normal vector, n, this thing here, not the normal vector, more rigorously, it's the vector that's been normaled, being turned 90 degrees, is actually the gradient of that function what we found, that we're trying to find. So, by the way, this field, as we've seen earlier, is normal to direction field. It's a 90-degree rotation of the direction field. So, what we can do is that we can start plugging in numbers right now. Remember that thing, the direction field vector that we found out earlier? Yeah, we're going to use that now. So, when we rotate the vector by 90 degrees, this is what happens. You swap it and you put a minus in front of it. If you want, you can actually try to pause and ponder and find out if this is true by yourself. And mu is just a constant that corrects this all. This will be important later. So, we can actually put this and make it equal to the gradient vector. So, the gradient, how you interpret it is that it's a column vector with two slots. The first slot is the slope if you only change the time, and the second is the slope if you change the x. So, let's just work this out quickly, and, well, we are gonna integrate. Wait, hold up. Something's not right. Stop. Well, as you can see, unfortunately, life isn't that easy just yet. We can't just integrate the whole thing yet, even though we almost want to. Say, let's take a minute and step back here. What if the normal vector field looked like this? What function would come out of this? This is the function that came out of it. And, well, here it is. As you can see here, the function is actually discontinuous. You might think, oh, that's not a big deal, right? Actually, it is a big deal. You realize that's a paradox, right? If you keep increasing, but still end up in the same place, well, yeah, you do realize you're kind of not stuck in a loop-ish, right? If you look at a 3D structure. More rigorous way to say this is that a function, you can't find the derivative of a function if it's not continuous, like in this case. Therefore, well, the gradient is written in derivative, so you can't find the gradient using this. So, basically, a field can only have a function only if something called the curl is 0. A curl is just a math operator, measures the curliness of the field. As you can see, if the field curls around or rotates around itself, it won't have a function. So the trick is that instead of using mu as just a mere constant, it's actually a function. Wait, hold on. Why is that remotely even equal? What? So I'm going to show you a little bit of a trick here that can actually bypass this. So, as you see, well, we can write the equation like this, almost separating and integrating it, moving around it, but saying it all equal to 0. Actually, when you move it around, it still equals 0 anyway. So, what you can do with this is that, well, as you can see the components here, right? They actually look like the components from our normal vector. We multiply by mu on both sides of both constructs. We find that you can just put mu just about equals to anything. It'll be 0 anyway, so it doesn't matter. Still, mu can be any function. So, here's the final stretch. So, rotate the vector field, rotate the direction field, then put equal to the gradient. Then we almost start integrating, but before we integrate, we solve from mu that makes the field not rotate. And all of that can be used to find phi. Plug in our equation, the differential equation we have, we can find the phi explicitly. And now, in the final stretch, we set everything equal to the initial conditions at time equals 0, and then we can solve for x of t directly. And indeed, this x of t, this pseudo-charge thingy, is actually the form of the solution of how much charge will remain in the system as time passes by, as we plug this into our outlet. And for those of you who are really curious, here's the solution for if we use different frequency for the voltage. Well, go try your hands at that. Try proving that formula up there true or false, or maybe I've done something wrong. So yeah, we're kind of done. So, but before we go, isn't this the solution to this problem really elegant? But just using geometry, you can literally shop off either just approximating or mindlessly fiddling with calculus and solve this problem using just algebra. Connecting calculus to geometry and geometry back to algebra. Think of how much energy both you and your computer save. You don't realize that iterating a lot of times just consumes a lot of energy, right? The best thing about this method we use here is that it doesn't just apply to our capacitor alone, but also applies to just about anything that you can't separate and integrate, provided it's first order equation, of course. In other words, if there is a function of t lying around, if it's just a function, the derivative is just a function of t and x of t, where t is including the x, things from strings to fluid dynamics to escape velocity calculation, even to calculating the metabolism or modeling the metabolism of things inside of cells. The last example tells me this. Even if this piece of math feels like a really niche thing, it's beautiful, yes, but it's really niche for mathematicians, it's actually useful to us. In fact, it's even happening inside of us right now. Mathematics, to me, is truly elegant and infinitely reaching, even more than we expect. Thank you everyone for watching. Keep learning and keep discovering. Goodbye.